Okay, we're in section 4 of the notes, and this is the section on trigonometric identities and equations. So, whether you're in my class or maybe another instructor using my notes, we want to encourage you to try to follow the structure of this document. All right, what does that mean? In section 4, we're going to cover basically trigonometric identities and equations. It's a tough section. We're encouraging you to follow this section. I'm breaking it into 3 separate pieces. That is simplifications, because they're related to both verifying identities and to solving equations. And we'll certainly go through that, right? Once you finish section 4, that is, attend the lectures. Now, whether you're doing that in real time or you're watching me at the end of the week, but you need to attend the lectures. You need to watch me do the examples, and then you need to do the supplemental exercises on your own. I will, of course, publish my solution to those problems, and I'll do that at a whiteboard for you. All right, and I'll publish that for you to watch if you want to watch it. All right, but you got to get through it all. And once you get through it all, what we'd like you to do is finish topic 4 in the WebAssign. It really comes out that simple. So what I want to do is I want to briefly go through what the lecture is going to look like. And the lecture is going to look like this. The first thing we do is we're going to basically just review what we know about these circular functions. Now, what are we talking about circular functions? We're talking about a circle centered at the origin, right? That's coming from Math 100. Equation of that, r is a positive number, x squared plus y squared equals r squared. Really simple, centered, a circle centered at the origin. Then we talk about the definition for the angle theta that's being rotated in standard position. We talked about the definition for the sine function, cosine function, tangent function, cotangent function, secant function, and cosecant function. Knowing these definitions is going to allow me to generate a bunch of very simple facts about these relationships, all right? And we'll go through that, all right? Some things we're going to talk about is notationally. I realize some things may be confusing to students, but we're going to try to clarify any confusion. How things are going to be typeset for you or printed at the whiteboard. We're going to talk through fundamental identities. It should be rather simple to do that. We're going to talk about Pythagorean identities. It should be rather simple to do that as well. I also want to point out in the notes, for those students that have a trouble following long lectures, you can actually watch a spot video. If that helps, that's what you're going to be doing then. You're going to watch spot videos. All right. We're going to talk about even odd identities. How do we get those? Basically, we're going to get those by understanding the graphs. We know what an even function is. We know what an odd function is. We know what the trigonometric functions look like from graphing and prior sections. Again, you need to study that material to know that material. If you haven't studied the material, it's just another thing you're adding that is going to be another thing you add that you can't understand either. You got to have a foundation. What's a foundation? Week by week, it requires a lot of study from you guys, all right? We're also going to talk about cofunction identities. The way I basically relate those things is by looking at triangles, all right? These are valid for all theta though, all right? We're going to talk about simplifying a trigonometric expression. We will go through examples. We will talk about proving or verifying a trigonometric identities. We'll go through examples, and then we'll talk about solving trigonometric equations. But the skill set builds on this. Can you simplify a trigonometric expression? Can you verify an identity? If you can, and by the way, if you have a pass with what we've done with the simple triangle problems and the definitions of the various trigonometric functions, and you've done the graphing, solving a trigonometric expression would be relatively simple. But again, I'll go through it in lecture. It boils down to only 3 problems though, right? That the sine of the angle will equal a number, the cosine of an angle will equal a number, or the tangent of an angle equal a number. Every single equation we give you boils down to those 3. It's really that simple. All right. So we'll get to the problem set. But before I do that, I want to go to the whiteboard. And as I go to the whiteboard, it would be great if you had your notebooks out and you had access to the notes and you're willing and ready to do and listen listen to what we're going to present to you. We do another share. Okay, I'm at the whiteboard. Let me go back through the pages, and that's where we kind of stopped right there, right? So let me go back and give me 1 second. Okay, so let's just review the circular functions. And as I do that, it really it's just a review. It's not new material. It's something we've done in the past. Again, if you're not putting the required time in, you might look at this and say, I don't even remember looking at that. Well, maybe you didn't look at it. You got to go back and study that. We're in section 4 of the notes now. And again, roughly speaking, you spend about, I don't know, maybe I'm going to say if you're well prepared for the class, that is, you've done well in other prior math classes, about 10 hours per week on this class outside of the classroom in study time and homework time. All right. All right. Let me go get my picture. A really basic picture. We've done this many times before. Something like this down where this was the x-axis or the abscissa. This is the y-axis or the ordinate. And we put a circle down. Now again, whether it's a unit circle or a circle of radius r, it really doesn't matter. And there's a point in the circle. What's the point? X comma y. There's an angle here, theta, in standard position. And the bottom line is, what's the relationship that we know about? Well, it's a circle centered at the origin. And that relationship, when you learn in Math 100, it's a Pythagorean relationship. X squared plus y squared is equal to r squared. Then we had 6 separate definitions. And those 6 separate definitions had to do with this picture over here. And what I mean by that is you have to understand that, y is the ordinate and x is the abscissa. Theta is the angle in standard position, and r is the radius of the circle centered at the origin. All right. So what definitions do we give you? These over here. These definitions absolutely need to be known, right? They need to be known. There's 6 definitions. You would need to know the definition of the sine function. Now, when we say sine function, sine takes an argument theta and it returns the ratio y, which is the ordinate over the radius. The cosine function is defined as a function of theta, and it's defined as the abscissa over the radius. And again, this is for a circle centered at the origin. The tangent function, tangent is a function of theta, and it returns the ordinate over the abscissa, right? The cotangent function, well, I'll be honest with you, what's nice about these guys over here is that I'm starting to realize that they're just reciprocals now, and I'll go through that in a second. So I'm going to claim over here, if I looked at it, y over r, the reciprocal of that would be r over y. So you should identify now that sine theta and cosecant theta are just reciprocal functions. Now, if you look at x over r, its reciprocal will be r over x. What am I saying? The reciprocal of cosine is secant. Really important. All right, let's keep going. And let's do this one. Y over x, its reciprocal will be x over y. What am I noticing? Well, the tangent function, cotangent, they're just reciprocal functions, right? This is the basis of everything that follows. Let's go to the next page. All right. Some things are confusing to students. By the way, I can't change the way the world works, but a lot of students are confused by notation. I'm going to pull this on the side. I'm going to talk about it. You are going to see functions being squared. If it were my world, the way I would write that down, I would write it down this way over here. If some function's being squared, I'd put that function in parentheses and I say I'm going to square it. Now, what does that really mean? It just means the function's put down twice. It could also be written this way over here. Here's the way that everyone else in the world writes it, though. They put the 2 on the end. What does it mean? The sine function is being squared, not theta. The sine function is being squared. If that's confusing you, you need to pay attention to that and make sense out of the notation. That notation is going to come up a lot. So if you see me write down something like this over here, what does it really mean? It means tangent of theta times the tangent of theta. Well, for my world, I just simply write down tangent of theta. The whole thing is being squared, so forth and so on. That goes for higher powers too, by the way. All right. What's a convention? Well, almost everyone in the world would write this one down instead. Be aware of that. If it's confusing you, try to get that confusion resolved. All right, let's go to the next one. The next one are these fundamental trig identities. All right. Now, what I'm going to claim over here is I'm talking about these guys over here. What I'm going to claim is that I'm going to say some of these things are really important for me. All right. And what's important for me is to know what we just discussed is that, the sine and the cosecant are reciprocal functions. That's what it says right over here. But I could also write that down, a different way. And I'll tell you the way I could write that down, which may seem bizarre to you. I could write this down a little differently. I could simply say the sine of theta is the same thing as 1 over the cosecant of theta. They're reciprocals. I could write that down. Let's keep going. Let's see if we can do it. Let's go to the next one. And the next one is that secant. What is that going to be? It's reciprocal of the cosine. Well, I'm going to write it down a little differently. I could also write this down as the cosine of theta is 1 over the secant of theta. Right. Now, where they come from, the definitions we just talked about, those reciprocal things we just noticed before. We wrote those things down. All right. Now, I can write the next one down. A little confusing. I guess I could do it. The cotangent of theta just reciprocally related to tangent of theta. Let's write it down a little differently. Whoops, sorry about that. I can write down the tan of theta is equal to 1 over the cotangent of theta. All right, now the last three, I'm going to point out, not last three, last two, I'm kind of looking at it and wonder, why did they do that? And I'll tell you why. Initially, it is in your interest, whenever you see any function other than sine or cosine, you need to rewrite it in terms of sine and cosine. All right. So what I want to do is I want to start to circle things that are going to be incredibly important for you to follow. All right. And certainly we'll go through examples here. If you see cosecant, I am going to recommend that you write it in terms of sine. If you see secant, I'm going to recommend you write it in terms of cosine. If you see cotangent, well, I'm not going to recommend that. What I'm going to recommend is if you see tangent, you're going to write that in terms of sine and cosine. And if you see cotangent, you're going to return sine and cosine. Let's go through this, and I'm going to go through it one at a time. Oops, sorry about that. All right, let's write tangent down. Now, someone says, how'd you get this identity over here? Well, let's write our definitions down. All right. Now, how's a tan of theta defined as far as the abscissa and ordinate, with the understanding that the abscissa is x and the ordinate is y? Well, the tangent of theta is going to be y over x. Now, what's the sine of theta? And again, going back to the definitions, using that circle centered at the origin, where the abscissa x and the ordinate is y. What's it going to be? Y over r. And what's a cosine of theta? Well, if you go back to the definitions, the cosine of theta is going to be the abscissa, which is x, over the radius r. Well, if you multiply top and bottom of that by r, you would y over x. So certainly y over x does equal y over x. This is a super important identity. Our goal when you see functions that are not sines and cosines is to write them in terms of sines and cosines. So if you see tangent, you're going to write down sine divided by cosine. Now, granted, someone says, am I always going to do that? Well, you're going to get more familiar, and you may not always be doing that. Right, now where's the other one come from? I'll write it down for you. The cotangent of theta is just a reciprocal of the tangent. So what does that mean? It's going to be cosine theta over sine theta. This is also important. All right, let me just point out the important ones for you. Important, important, If you see cosecant, write it as 1 over sine. If you see secant, write it 1 over cosine. If you see tangent, write it as sine over cosine. If you see cotangent, write it cosine over sine. All right, let's go Pythagorean identities. I don't like memorizing things. However, some students do. What I'm going to claim, I'm going to pull it on the side. And we're going to derive these 3 over here. All right, let's go back. I'm going to talk about the story. And what's the story? It's the story, same story over and over again. X squared plus y squared is equal to r squared. Okay? And where's that coming from? It's a circle centered at the origin, where x is the abscissa, y is the ordinate, and r is the radius of a circle. We know all definitions to that picture for sine, cosine, tangent, and the reciprocals, cotangent, secant, and cosecant. What I'm going to do is divide both sides by r squared. Someone says, why would you do that? It could be pointless, but it's easy. So what do you get? 1. That's easy, right? Now, x squared over r squared is simply going to be x over r squared. Y squared over r squared is simply going to be y over r squared. Now, do you remember what the definition of x over r is? Again, do you understand that x is the abscissa? Well, that's going to be cosine. So I'll write that down for you. Cosine theta, and theta is in center position. Do you remember the definition of y over r? Well, I hope you do. That's going to be the ordinate over the radius, and that's sine theta. We do write it a little bit differently, and I want to tell you why that is. The world writes it that way. How does the world write it? This way over here. All right, let's take another one. I'll write it down for you. X squared plus y squared equals r squared. Now, what am I going to do over here? I'm going to divide both sides by x squared now. And what do you get there? It's really not bad. It's going to be 1 plus y over x squared and r over x squared. Now, again, you may not say, I don't remember because I haven't been studying that hard and none of this really makes any sense to me. But you should have the definitions down. All right. For example, I think I probably should know the tan of theta. And the tan of theta is going to be the, let's see, ordinate over the abscissa. I think I should know that one. And the secant of theta, that's a reciprocal of cosine, right? So it's going to be r over x. Well, now I'm seeing it. What do I see? 1 plus, what's y over x? Well, it's defined as being tangent. Theta, that's being squared. And what's r over x? That's being defined as secant. And that's being squared. Again, how does the world write that? Again, I'm not in a position to rule the world here, but they write this way. Be aware of that. You need to know that. All right, let's go to the next one. I wonder what the next one's going to be. Let's write this down. And I'm going to write down x squared plus y squared is equal to r squared. That just keeps popping up and over again. So, I divide it by r squared. I divide it by x squared. Now I think I should divide by y squared. So I'm going to divide by y squared. And what do you get? Well, you get x over y squared plus 1 equals r over y squared. Well, let's write some definitions we have down. All right, so I don't know what the definition is, but I guess I should write them down for you. Then cotangent of theta, that's going to be the abscissa, which is x over the ordinate y. And I guess I could write down the cosecant of theta. And the cosecant of theta is going to be the radius of that circle centered at the origin over the ordinate, which is y. So what's this guy over here? Well, if I looked at it, x over y is cotangent theta squared plus 1. And what's r over y? That's cosecant theta. That's all being squared. I don't really have much issues with this, but some people do. That's the way the world writes it over there. So let's point this out. We just derived these three things over here. They need to be known. They need to be known. All right, let's go to the next thing. And we just look at the notes. So we've talked about these, really basic fundamental trigonometric identities or reciprocal identities. The Pythagorean identities, we just did that. And now we're going to move on to this business over here. And I got to be honest with you. If you have not done the graphing exercises, this is another thing you're piling on your back you're not going to understand. But I want to point out when you took Math 119, you talked about the defining features of even and odd functions. What's an even function? A function that is symmetric with respect to the y-axis. Which trigonometric functions are even functions? That is symmetric with respect to the y-axis. I'm hoping you realize the cosine function is symmetric with the y-axis. What other function is symmetric with the y-axis? Cosine's reciprocal. Okay, if you look at the cosine curve, it has a folding symmetry about the y-axis. If you looked at the secant curve, it has a folding symmetry about the y-axis. Even symmetry is the simplest type of symmetry. Even symmetry, what is it? F of x would be identical to f of minus x. This is something you learned in Math 119. So here's the deal. When you're looking at that, that's all I wrote down over here. I wrote down the cosine of theta is identical to the cosine of minus theta. And the secant of theta is identical to the secant of minus theta. Now let's talk about odd functions. Now odd functions is what's called a point symmetry. What's a point symmetry? It's an origin symmetry. So odd symmetry is often called origin symmetry. Something you did in Math 119. All right? So let's just talk through the visual of it. So which of those functions is symmetric with respect to the origin? That means there's a folding symmetry through a point symmetry through that origin. And the functions that are going to be odd symmetric, and again, you'd have to know the pictures to know that, the sine function's odd, its reciprocal is odd, the tangent function's odd, and its reciprocal is odd. All right, let's write down what odd looks like. And these are the tests that you were given in Math 119. F of x equals minus f of minus x. This could also be written as minus f of x equals f of minus x. We're going to use this one here. So what do I do? Let's put this down over here. So I'm going to say the opposite of the tangent function is the same thing as the tangent function of minus theta. The opposite of the cotangent function is the same thing as cotangent of minus theta. All right. The opposite of the sine function is the same thing as the sine function of the opposite of theta. All right. I'm sorry. I got to put this one down too. You got to know those two. Someone says so much to know. You have to study. It's tough. We're not saying it's going to be easy for you. Let's go to the next page. And the way I like to do these things over here, I'm not going to say it's the only way, but I want to point out that we're still rusty on this. I mean, looking at the radian, I'm just going to write down, that 90 degrees is the same thing as pi over 2. And I'm going to go with it. I'm going to go with the degrees. So if you're reading through this, they talk about, a complement. Well, before I go through that, I want to point out what I mean by that. If you took a triangle over here and I put theta over here, it's a right triangle, what would the angle over here be? Well, it would be 90 degrees minus theta. This is what's known as a complement. Okay? So if you were to write down the sine of theta, I'll write sides down for you. I'm just going to, arbitrarily label these things as being, I don't know, simple stuff over here like A, B, and C. You get the idea? So if I wrote the sine of theta down, you're looking at it and, like it's properly oriented, it would just be A over C, right? What's the cosine of 90 degrees minus theta though? Well, I have to say this for a lot of students, this is difficult because we're looking to say, I don't even think I could do that. You'd have to twist that triangle around to get the A to be the abscissa. And you could do that. And what would you get? A over C. What did I note right over there, right from the get-go? That sine and cosine are related by being a complementary. All right? I'm going to circle that one where you see it, and you see that, whoops, sorry about that. You see that right here. All right? And now what I'm going to do is I'm going to write another one down. I'm going to write down the cosine of theta. Well, what's the cosine of theta? That's going to be B over C, right? And I'm going to write down the sine 90 degrees minus theta. Well, again, I'm looking at the same picture, and I got to twist that around a little bit, and then that would be B over C again. Again, I'm twisting around, so it looks like my diagram that I want. Let me just show this one. You get it? Let's put another one down. Let's put down the tan of theta. What's the tan of theta? A over B. Well, let's write down the cotan of 90 degrees minus theta. Again, I'm looking at my picture, I'm twisting it around a little bit, but that's going to be A over B. So what do we just show? The tan of theta is the same thing as cotangent of 90 degrees minus theta. I think you get the idea. These were all the co-function identities, and you could certainly do the other ones just by simply looking at a right triangle. They're fairly simple to do. Again, a lot of this thing just boils to a froth at this point, and you say, I can't get all that stuff. That's where the study department comes in. You got to start to study. You have to start to think. It takes effort, though. No one's going to be perfect at it. It takes time to get good at something. All right, we're going to talk about simplification, which is really the next topic up. And it's one that you want to master. All right, I'm going to read it to you. It says, to simplify a trigonometric expression, we use the simple trigonometric identities to rewrite it as a simpler expression. We'll go through examples. Usually it is best to write a trigonometric expression in terms of sines and cosines. I can't say that enough times. It's usually best to write things in terms of sines and cosines. However, as you develop experience, you're going to start to recognize things much more quickly. All right. Our goal, though, after simplifying something is at the end of it, it should be a very simple statement at the end. By the way, they may be conditionally true, but we're looking for simplifications. Again, they may be conditionally true. So most simplifications will be quite straightforward and will often mirror what you did in basic algebra. Addition of like terms, multiplications, and reductions, just like you did in algebra. All right, let's go over proving identities. A little confusing, but again, we'll go through examples. And we just did the simplification part. We talked about it. I'm not saying we did examples. Now we're doing this thing over here. I'll read it to you. To verify that a trigonometric equation is an identity, we transform one side of the equation into the other side by a series of steps, each of which is itself an identity. Initially, we will work with the simple trigonometric identities only. Here's the general technique. Let's go through it. Start with one side. The way I do this is I identify the side I'm starting with by putting a circle around it. It says over here, it is usually best to choose the side that appears more complicated. And why is that? It will allow opportunity in rewriting it. Number 2 step, use known identities only and try to use simple, obvious steps that bring us closer to the other side. What we're really trying to do is show one side that we picked is identical to the other side. And yes, we will go through examples. Converting sines and cosines can in fact be very helpful in most circumstances. So here's the deal. If you're seeing something, maybe if you convert everything into sines and cosines, life will get easier. Not always. All right, last but not least, let's talk about this. Solving trigonometric equations. If you can't simplify a trigonometric expression or verify an identity, you're not going to be able to do a trigonometric equation. Furthermore, if you can't graph, you will have no understanding of what the solutions mean to a trigonometric equation. You need to be able to graph. So it depends on your past now. So you should know what it means to solve for an equation for x. Now in the past, when you solve an equation for x, they're pretty simple stuff, by the way. You have linear equations, quadratic equations. When you took 119, you had cubics and so forth and so on. Maybe log equations, rational equations. You had some choices, right? Exponential equations. You have many techniques, by the way. Those techniques should be probably still maintained. My claim over here, though, is that we're really going to boil this down to really simple cases. And let's talk about those 3 simple cases. So the 3 cases you're going to see in this classroom, no matter how bad these equations look, they're going to boil down to this. The sine of an angle equals some number, the cosine of an angle equals some number, or the tangent of some angle equals number. So let me point this out. No matter how complicated they look initially, they boil down to these 3 very simple problems. Then it comes, how do you solve those problems? That's what we're going to go through when we do examples. I want to point out that x is an unknown angle. K is a given numerical ratio. No, it's something we know about in the past, right? So I want to point out for both sine and cosine, the ratio K should be on an interval between -1 and 1. And why is that? Well, if you think back to the graphs, our graphs never exceeded -1 and 1. Never did. They're in between. But there's no restriction on the tangent. Why is that? The tangent has a range of all real numbers. Okay, let me go to the next thing up here. So first thing, you're going to boil down to that. Next thing, once you get one of these forms, you should graph one cycle of its related curve and locate the angle x that produces the ratio k. You'll see me go through examples. But here's the problem. After you go through examples, you probably want to come back and read this to know why we're doing that. All right, let's go to this one. You should note that these functions are periodic. What does that mean? They keep repeating themselves over and over again. So I'm of the assumption that they keep repeating themselves over and over again, the solutions will keep repeating themselves over and over again. So you should note that both the sine and cosine have a period of 2 pi. That means they keep repeating itself every 2 pi. And the tangent repeats itself every pi. We'll certainly go through examples to illustrate those points. Okay, the trouble most students have is getting the equation into the proper format. We'll do that as we start to work through problems though. Once you see one of these equations, it is usually quite straightforward to solve for the variable x, and we try to keep it really simple, right? Really simple. We're not trying to confuse anyone. All right, thank you.